Power integrity problems are a good way to make yourself miserable. It is an intermittent problem always. The problem reported can be really weird and hence really difficult to track down, and it's almost guaranteed to involve a layout change, which we don't want to do because the board's probably already in production because it's so intermittent that was never caught during prototype stage. So to avoid all that mess, we're going to talk about in this video what to do. So on the left here, I have the simplest of circuits right here. And then on the right, all I did was add the parasitic inductance. The formula is just same thing for an inductor. That's it. On this channel, we try to keep the math easy. So we have inductance here, and then we have DIDT here. I'm going to talk about DIDT in another video because that gets complex. We're just going to keep it to the L terms here. So this one here on connected to power is pretty well understood even by newbies about what to do even if you don't fully understand it. This is where you get into short traces, wide traces. Don't forget the decoupling caps. You need them. And then the bulk capacitors. So I don't want to linger on that topic just because most people do the right thing for there. Repeat, most. This board I'm working on, oh goodness. But that's another story for another day. So for this one here, okay, first of all, nobody ever really thinks about the return path. So everybody's tunnel visioned up here, but they don't really think about down here. About, okay, all right, power's in my component and I got a via to ground. Cool, done. Well, no. Because of all the stuff up here, you can say that it's engineered. Your return path needs to be just as engineered. So this is where we're going to spend the bulk of our time because we can get a lot of improvement out of here. So what we're going to do now is we're going to go into one of my favorite programs. It's called Saturn PCB Design. You can get it from these guys. It is free. So, and I use it all the time. What we're going to do here is we have our traces here. We have our ground plane right here. And what I did, the width, we don't really care about for this exercise, but we're talking about the height from here. So I did 62 mils just to do a 2-layer board. So that right here is the inductance. That is the number we care about. So if we go from a 2-layer board to just go to a 4-layer board, that number gets cut in nearly half, just from going 2 to 4 layers. So that makes me happy. That's actually what we'll go into is this is actually a pretty easy change for some big benefits there on the ground. Okay, but this is ideal. This assumes your ground plane is adjacent to your signal layer. So that would be this guy right here. So this is a typical 4-layer board stack up, signal, ground, power, signal. Many designs work with this, but as I said, I want to over-design. So also during the design process, especially during layout, I've got all these rules and all these things I'm thinking about inside my head in order to get the design to work, to look good, to be manufacturable and all that. So I don't like this where, oh, keep the high-speed signals here and keep, anything else that's not high speed down here. I don't like that. So that's one weakness of this. Another weakness of this, which I'm going to show here, is particularly this bottom layer. So focus on the picture here. Signal goes in via does its thing on the bottom layer, then the return layer in the back. This is where we go a little bit crazy. Go here, but in order to do this effectively, it's going to find its way to a decoupling cap. So at this point, you've already lost me. Just from an inductance point of view, because you have a via there, you've got a via there, and then this capacitor is going to have its own inductance. But I think that they aren't going basic enough. So I'm going to pull up a little bit of a layout here. We're going to pretend that doesn't exist for now. We'll bring it back. So this is a decoupling cap. And actually, before I do what I'm going to do, what I want to do here is that is about, if we go center, let's round up, 250 mils away from my nearest decoupling cap. And as we saw from our Saturn PCB, that's a lot of inductance right there. So the way to solve that would be to do this. Add a decoupling cap in your schematic, put it right next to this via. So this is right with that stack up, but after reviewing hundreds of boards, I have never seen this, ever. I have never seen anybody do this. Like, it just isn't done. So on dense board designs, dude, sometimes I have trouble fitting vias in, let alone another capacitor. So I don't think this is reasonable, but furthermore, sometimes you gotta design for politics, design for ego of other engineers that are gonna review this. So even if you're right from a technical point of view, they're gonna say you're crazy. And frankly, I don't think this would survive a design review, even if it is technically the most well thought out plan for this stack up. So for that reason, let me scroll down a little bit. For that reason, because of the weirdness here and because of because I just won't be able to do decoupling caps. So I always stick with 2 ground layers in the middle. Always. I have never seen a case where I had to deviate from that and actually have a power plane. So, and let me even show you why. So we got to go back to here. I have got a design where, this is where we're looking, by the way, where my fault current was 50 amps. You are, in your designs, you are checking fault conditions, right? Fault current. Good, easy example I do all the time. If I've got a motor in my product, I stick a screwdriver in there and stall the motor and see what happens. Because you know some dumbass is going to stall the motor somehow, some way. So we got a plan for that. Anyways, so if we do these, we can get significant current out of not much thickness here. So, but wait, what if we do an internal layer like what we're talking about? Well, okay, you might say, you know, you've got a huge plane and whatnot, so you can do significant. So yeah, that's fine. But point being, I can do it on an external layer. And because of the thicker copper, and because this heat can radiate into the air, I can get more current out of this. So it's not as big of a deal. And then if we just go to 10 here, you know, we can do over an amp on an external layer. So, and this is with the 10 degree C rise, which is pretty conservative. We can go higher. we can potentially go a lot higher. So in this, you know, we aren't even at this 130 with if you add both of these. So we could even go higher. But point being, I do not buy that you need to have a power plane. That is not mandatory. So what I do is if I do power polygons here, and I put them on both sides of the board, and I use tons and tons and tons of vias to basically make it as one. So I get the advantages of external layers, thicker copper. I get the advantages of it's exposed to air, so heat can radiate out. And then I do the vias that make those two layers into one, kind of effectively. So now that I have two grounds, this also helps with ESD, by the way. So there's so many reasons to do two ground planes. So if this is also ground, now I can have high-speed signals on any layer that I want. I don't have to worry about it. There's so many advantages to just having a second ground plane. So, and as far as this, let's get back up to it. Instead of dealing with this weirdo cap and return that nobody is going to ever approve in a design, even though it's right, we can just have a ground via right next to it. So you want this spacing small, of course. Then height's already reduced because we're going to a 4-layer board. So like this, and it's so easy to do. Like what I do is I'm usually on, I do my ground planes first in a design. That way when I need a signal via, I can just go pop right there, done. So I don't obsess over this distance. Dude, if I click and I'm just like right there, whatever. Because I know that anything I do here will be so much closer than here. So in this line of work, for something like this, just doing this at all will annihilate most beginner and intermediate engineers. So there's that. Another advantage of having two ground layers is that for my, if you want to convert a 2-layer board to a 4-layer board, the easiest way is just two ground planes. If I have a power plane, now I got to connect to it and worry about that. But if I have two ground planes, well, you're already going to have vias and stuff like that. So you can just pretty much add it, and then you're done. So some people might get me on that. It's like, well, you may want to, while you're there, you may just want to add more ground vias to tie them all together better. Yeah, okay. All right, fair enough. Okay. Last thing I want to show you, this isn't for lowering L any further. This actually is for increasing C, but it was in the same video. Notice how they did power pores right here. So apparently what they did right here, this right here. So adding these power pores can reduce impedance significantly. So I thought that was worthy of note. So not only that, so what your board manufacturers are going to want is a balanced board. So your inner layers are going to be whether it's power signal or not, that part is balanced because it's just a big piece of copper at the end of the day. So, but with your outer layers, your signal layers, that can be a lot different. You got components here, some signals there, some signals there. So your outer layers may not be balanced. So if you have extra space, you should probably if you can, do a power pour to balance out your board a little bit better, and then lower this impedance here. So that's kind of a win-win for everything. So kind of talked a lot in a short amount of time. So to sum it up, go to a 4-layer board if you're on 2. have two ground layers, signals on the outside, components on the outside, then power here also, and this will solve many issues on your return path. If you cannot change Stackup for any reason, remember, we just talked about, hey, sometimes you got to design for politics. Sometimes you got to design for egos. See if you can put your vias close to your decoupling caps if you cannot switch your Stackup. So I think that's a good review for today. So remember, we're gonna, next video, we're gonna be talking about this DIDT terms. So stick around. Thanks for watching.